And here we go. Okay, so this is calculus limits and derivatives, day number 6, mean value theorem, Rolle's theorem. Okay, Rolle's theorem is don't be stupid version 2. Ready? If I have two values whose output is 0, let's say this is C. What is f of C? Oh, I don't want C. I want A. What is f of A? 0. What is f of B? 0. If a function is continuous between the two, doesn't matter what it looks like, all it says is that there is some C that exists such that, I'm writing exactly what's above here, f prime of C has to equal 0. Therefore, means the derivative has to equal 0 somewhere in between. Because it has to, if it goes up, it's got to come back down. So it's got to hit a maximum. If it goes down, it's got to come back up. It's got to be a maximum. Someone said, what if it's a straight line all the way across? Is that continuous? Yes, guess what? There's an infinite number of points where the derivative is 0. Oh. Too easy. Okay, so on the next page, here is the formal proof of Rolle's theorem. I'm not going to do it because, 1, I don't want to. Because it's don't be stupid version 2, right? And 2, because that looks like a whole lot of yuck. Someone did us a favor there. But that's Rolle's theorem. So I think of Rolle's theorem as you got to roll over a max or a min at some point, right? Roll over a max, right? Oh, potato problem. Thank you much. Okay. But Rolle's theorem just says that between two zeros, there's at least one spot, at least one, where the derivative has to equal 0. Okay, cool. Let's talk mean value theorem. Okay, before we talk mean value theorem, I want to take you on a little trip to a place called I-70 in Kansas. You ready? I-70 in Kansas. There's a reason. There's a reason. Okay, I-70 has an entry ramp and an exit ramp and a certain distance in between it. I think it's between Topeka and Manhattan, and it's about 100 miles. Okay, and the speed limit on I-70 is 70. Sweet. So how long should it take me to get from Topeka to Manhattan? 100 miles, right? The speed limit is 70 miles an hour. It should be a little bit, I could make it in an hour. Wow, okay, that's a great question. What if you do make it in an hour? Let's say at Topeka, there's a little camera that says, snap Zane's license plate, right? Zane, perfect push-up, right? It takes a picture at 10 o'clock, and at 11 o'clock takes another picture in Manhattan. Ooh, what's your average speed? Dang fast, right? Dang fast. Okay, the mean value theorem says this. The mean value theorem says this. This is 100. What do I want here? Yeah, 100, right? This is time. This is time. This is time. So Zane left at 0 minutes and got to Manhattan at 60 minutes. And in the meantime, he traveled 100 miles in the meantime. So whatever Zane's travel looked like, well, at first you can't all of a sudden terminally velocitate yourself. That's not a term. But you can't go from 0 to 100 right now. Terminally velocinate. So Zane probably did this, right? And then maybe at the very end, he was like, screw it, I'm going 120. Right? So along this line, this is distance. This is distance. Okay, fine. So what, okay, so what would, this isn't Zane then, is it? No, because the slope represents the speed, right? The slope represents the speed. So he went really dang fast here and then stopped for a burger. got pulled over, and then said, "Oh gosh, I gotta get there by the time I gotta get my hair cut." Boom. Okay, let's come up with another scenario. Let's come up with a scenario. Yeah. Mr. Fry to the roller garden. Fry, I hope you listen to this video. Okay, let's say the roller garden is in Manhattan, okay? But let's come up with a different scenario. Let's talk about this for a second. Okay? Boring. 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 That's pretty boring. What does that mean? They're going 100 miles an hour the whole way, right? They're going 100 miles an hour the whole time. Okay, so let me tell you a short story, and then we'll try to draw the line that goes along with it. Okay, I start out and I go about 100 miles an hour, and then I slow down a little bit because I'm like, oh crap, if I get there too early, the cops who take the time on the two snapshots will know that on average I went 100 miles an hour. So I want to slow it down a little bit, right? So we're changing the time here. We're changing the time. Okay, and of course, how fast we go will determine how long it takes us to get there. So let's say I go 100 miles an hour. Okay, 100 miles an hour would be, of course, I gotta gradually go 100 miles an hour, right? And then I realize I can't get there too early. So what should I do? Slow down. So the slope of my curve has to decrease a little bit. Now my time is dependent, right? Now of course time's going to extend, but oh wow, I just accelerated. I said screw it. I got to get there for my haircut. Okay, so what is the mean value theorem? Well, I traveled 100 miles in let's just say 80 minutes. Let's say I traveled 100 miles in 80 minutes. The mean value theorem says this. It says don't be stupid. This is a continuous function because you can't go from 10 miles an hour to 20 miles an hour just teleporting into that speed. You have to continuously increase or decrease. Therefore, the mean value theorem says this. Take your distance, or it might be a different scenario. It might not be distance per time interval, but your time, reduce it. And what do I get? Is that 5/4? Okay, so I get 1.25 miles per minute. That tells me that the slope of my line has to be 1.25 at least one place on my sketch. Could it be at multiple places? Sure. Let's say that this right here is a slope of 1.25. And at least one spot, well, let's say maybe this one here too. So the cops aren't that smart to just go by time, right? Because they're not. Because you could go really, really fast for a while, stop at the gas station, hang out for a while, and then go really, really fast for the second portion of it. And your time might be the same as if you just went the same speed the whole time. Therefore, the mean value theorem tells us that. Your time tells us what your slow or your change in distance over time is at least one point during that time frame. Okay, mean value theorem. Cool. Mean value theorem, it is a requirement that not only is this function continuous, but differentiable as well. So Rolle's theorem just requires, well, actually I think Rolle's theorem requires both as well. It does. It does. Both have to be differentiable. Whereas intermediate value theorem, all we needed was continuity. Right? So this is version 3 of don't be stupid. If you take the secant line on a curve, at least one point on that differentiable curve will the slope be the same as the slope of the secant. There might be two, but for sure one. For those of you who are interested, here's the proof of the mean value theorem. And I do want to look at one thing. Check this out right here. Let's say we're talking temperature of potato. Or no, let's talk distance. Distance makes more sense. Distance makes way more sense. This right here This is just distance traveled. So this is like Manhattan minus Topeka, right? This is distance. What does the derivative represent? Speed. And distance equals speed times what? Time. Time. Well, from A to B, it took this long. Right? F of A and F of B was distance. Right? It went from distance 0 to distance 100 over 0 to 60 minutes. So this is just distance equals speed times time, which makes total sense because the derivative is just speed, which is distance over time. And if I write this out, the derivative is approximately f of b minus f of a over b minus a, which is just slope. That's how we equate it to. And speed and distance and time are just easier to think about than temperature and time and change in temperature over time because it's kind of redundant. Right? Am I recording? Yeah. Good. Okay. Does anybody want to do any planche push-ups with me? They're pseudo push-ups. Your hands are down near your hips and you push from your hips. You want to try it? Lauren's going to knock them out.